Has it started? No? Okay, it starts. Uh, let me see. Hold on 1 second, okay?ต้องไปหน้า44มันไม่ใช่หน้า44ใช่ไหมมันคือหน้า41ใช่ป่ะ42ใช่ไหมอ๋อคราวที่แล้วผมมีเพิ่มหน้าไปเป็นหน้า44ใช่ป่ะ
คือ42เหมือนอาจารย์พูดถึงไปคร่าวๆแล้วครับแล้วเพราะว่า we already did the questions on page 43 as well.
Okay, page 43 as well. Yeah, okay. Review before this one, right? This one we supposed to have FIR and II, right? Okay, futures. Okay, FIR and IR. FIR, you got finite length. Finite length impulse response. And IAR is infinite length impulse response. Okay. Okay. And okay, let me. Okay. So for the infinite length impulse response, we can write it as difference equations. Okay. We most of the time write it as difference equations. Okay. Like for example, here, this is what? X, right? We did that. We say it's equal to xn plus x plus xn minus 1 plus xn minus 2 plus until what? Infinity, right? So over here, the whole thing is yn minus 1. Okay, so we're gonna have xn plus yn minus 1. Okay, that's the accumulator, and this one is like the feedback. Okay, so our yn here is equal to xn plus yn minus 1. This is called the autoregressive. However, it is unstable, right? It's not BIBO stable. Okay, it's unstable. Okay, to make it more stable, we multiply by r. Okay, we multiply by r. Okay, and over here we see if r absolute r less than 1, okay, it will be BIBO stable. Okay, that's our conclusions, and then we did this whole thing, right? Okay, now we talk about if we add the moving average, okay, to it. Okay, this is the part that this is the moving average. Okay, this is the autoregressive. Okay, so the whole system is called ARMA. Okay, ARMA system. Okay, ARMA system stands for autoregressive followed by moving average. Okay, and over here we can rewrite the questions, right? Okay, we have yn, right? According to this, yn is what? Yn is equal to vn, okay, plus 0.2 yn minus 1. right? Because over here, okay, yn goes to the delay. This delay, usually I write z to the negative 1, okay? It's going to be yn minus 1 here, okay? And times that. So this is vn. However, this vn is what? According to this, it's xn here, right? This is 0.5 xn, which is this one, right? This one is 0.5 xn plus this one would be, this leg would be 0.5 xn minus 1, okay? This leg is xn minus 1, okay? Because this is to go through a delay. Delay, we got uz to the negative 1, and this is xn minus 1 times 0.5, okay? And therefore, we put Vn here and substitute in here, okay? We're going to get Yn equals to what? 0.5 xn plus 0.5 xn minus 1, and then plus 0.2 yn minus 1, okay? This is our ARMA system, okay? And you can see if I move the negative 0.5 here over, we got yn, okay, minus 0.5 and minus 0.2, okay? 0.2 yn minus 1 is going to be 0.5 xn plus 0.5 xn minus 1, okay? So to generalize this, okay, we can have y ak, okay? We can have ak, which is the constant terms times yn minus k. K start from n naught to n, capital N, and bk, okay, equal to summation of bk. Bk are like the what? This bk is like 0.5, 0.5 here. This ak is like 1 and 0.2, negative 0.2 here. Okay, and you can start from M0 to M. Okay. However, if the system is to be causal, what's the value of M naught and N naught? It cannot be negative, right? Okay, so this case is got to be more than or equal to this one supposed to be more than or equal to 0. Okay, on both. Okay, you can start from 0. Okay, because if you start from what? Some negative values. Okay, if you start from some negative value, for example, suppose if you summation k from negative 2, then you're gonna have what? You're gonna have a negative 2 y of n plus 2, which is non-causal, plus a negative 1 y of n plus 1. Okay, this one, negative 2, negative 1 is non-causal, right? Make it non-causal. If you want causal, it got to start from 0. Okay, and a lot of times we normalize it. Okay, a lot of times we normalize it so that a 0, okay, which is the coefficients of yn, okay, is normalized to what? Coefficients of yn normalized to 1, okay, usually, okay, the coefficients of yn is normalized to 1, okay. So in general, instead of the picture on top here, okay, it's changed into this picture, okay. So yn goes out, right, here. Okay, so it goes down to n, capital N. Okay, we start from 0, right? From n from 0. Okay, So this is the usual form. Okay, this is the usual form. Okay, so we're gonna have yn equals to what? This whole thing is Vn, right? Okay, this whole term here is Vn. Okay. No. No. I'm sorry. Vn is supposed to be the second term, right? Mm-hmm. Vn is the moving average part. Okay. Okay. Vn is this one, right? This Vn here is x1 b0 plus b0 x0 xn, right? b0 xn plus, and then this is the delay, right? So you got b1 x n minus 1 and so on. Okay, that's the moving average part. Okay, and for the for this part is the autoregressive part. Okay, however, okay, this system, okay, however, we learned previously that if you got subsystem H1 and then cascade with H2, what happened? If this is Xn, go in Xn, output is Yn. If you got two subsystems, H1 and H2, you can what? What can you do? Well, they convolute, but the convolutions, the whole system is convolution, right? But so basically you got H1 convolute with H2, okay? So basically you got moving average convolute with autoregressive, but it's also equal to H2 convolute with H1, right? That means you can interchange. Okay, you may interchange the subsystems. Okay, interchanging the position of the subsystems. So I could, this one is our H2 and this one is our H1. Okay, I can switch the two. And if I switch the two, this is what I get. Okay, this is our this is our H1 and this becomes our H2. Okay, you can interchange that. Okay, you can see the difference. Okay, you interchange the two. Okay, this is another form. Okay, and then with these, okay, you can combine these two together. You can combine this delay together. Okay, this one we assume, okay, this one we, well, normally, this one got to be an, this one got to be bm. Okay, this one we assume bm, we assume m equal to n. Okay, this one we assume m equal to n. Okay, assume, actually you don't need to be m equal to n. Okay, if n is equal to n, then you can combine the two together. Okay, and it becomes this systems. Okay, the system is called direct form to realizations. Okay, direct form to realization. The first system here, okay, this system here is called direct form 1. Okay, what's the advantage of direct form 2? Okay, direct form 2 is that it has what? Realization direct form 2, it reduces the number of delays. Okay, normally you're gonna have what? N plus M delays, right? The number of delay components is M plus N. Okay, but for this one, it's reduced to just the maximum. Okay, this one, the delay, number of delay elements. Okay, number of delays is equal to the maximum between M and N. Okay, All right. So it reduces. What's the advantage of the direct form 2 realization of direct form 1 is that direct form 2 has less delay. Okay, components. Which is good, right? As an engineer, you want to save costs, okay? If you want to implement it by hardware, okay? You don't want too many delays, okay? If you got so many delays, you got to waste a lot of money on it, okay? And what's the direct, oops, oh, oh, okay. Uh, Here for the direct form 2, okay, what's the equation for direct form 2? Okay, if you write this, okay, yn here, okay, yn here is equal to what? According to this leg, it's going to be b0 times wn, right? And then plus here, this is wn minus 1, right? W is plus b1 wn minus 1, right? Plus until the last one would be what? This is wn minus n, right? So plus until b capital N, wn minus capital N, okay? Which is this one. Okay, which is this one. And then you got to find out what wn is. Okay, that's the intermediate state. Okay, the wn according to this, okay, it's gonna be what? xn, which is this leg, and then add this leg, which is a plus a1, okay, wn minus 1, plus dot 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 until the last one. Okay, according to this, it's an wn minus capital N. Okay, according to the pictures. Okay, but remember our n and m. Okay, here if we sum b, okay, bk actually to m and ak actually to n. Okay, so b could be to m, okay, and ak to add sum until n. Okay, so in this case you could substitute this in there. Okay, substitute this in there, so the total would be yn is going to be a mess actually. Okay, yn is going to be summation of k from 0 to m bk, okay, but wn minus k, okay, wn minus k. Let's change the variable a little bit. Okay, hold on 1 second. Okay, need to plug in. Oops. Oh gosh. Okay. Okay. From these equations, okay, from this equation, we could have wn minus k, okay, but I'm going to use different k now. It's going to be, I'm going to change this k, okay, to j, okay, so this k is j, and this is aj, okay, so wn minus k, okay, this w, okay, it becomes n minus k because we want to substitute in there. Okay, so we're gonna have x n minus k plus summations of what? J from 1 to capital N, aj, w of n minus k, and then minus j. Okay, and that's what we're gonna have. So we're gonna have wn, which is this thing times x n minus k plus summation j from 1 to n aj w n minus k minus j. Okay, so this is the direct form 2. Okay, realizations. Okay, this is the direct form 2 realization. Okay, we got direct form 1, we got direct form 2. Okay, that's pretty much it. Okay, if I give you the diagram like this, okay, you're supposed to be able to come up with the equations. Okay, come up with the difference equations. Okay, if I give you direct form 1, it's easy. Okay, if I get you direct form 2, you might want to work out a little, okay, on the difference equations. Okay. Okay, the direct, but this one you got to replace it by another recursive function, is it? Yeah, it's going to be very difficult to do that. Okay, anyway. Okay, let's talk about similarly, okay, similar to the discrete time, okay, similar to the discrete time LTI system, okay, in continuous time LTI system, we can write it as ordinary differential equations with constant coefficients. Okay, I call it linear ODE with constant coefficients. Okay, LODECC. Okay, this is a linear ODE, ordinary differential equations with constant coefficients. Okay, similar to the okay, similar to this one. Okay, similar to this form. Similar to this form, okay, we just replace the well, actually we just replace the delay, okay, into y derivative, k derivative of t. Okay, this is will be x k derivative of t. Okay, same thing, but this one we start when it n equal to 0. Okay, we don't want to involve with the integral. Okay, so we start with this one, ak. Okay, y to the k derivative. Okay, this is y to the k derivative. This is the derivative, k derivative. Okay, y to the parenthesis, in parenthesis k, it means the k derivative. Okay, so this is also, this is a continuous time LTI system. Okay, in the form of linear ordinary differential equations with constant coefficients. Okay, for example, suppose if we give you this diagram, what is the differential equation that correspond to this realizations? Well, this one we're gonna do is differently. This y gonna come down because this one you do integration. Okay, this one we do integrations. Okay, so y, the top here will be y prime, this one here will be y double prime, and this one here will be y triple prime t. Okay, and how do we draw this one? So this yn would be what? According to the diagram at this point, uh, how would you write it? Okay, this one multiplied by 25, so we got 25 yt here, right? And this one we got what? Negative 7 y prime t here. Oh my. And this one we got what? 14. So you sum this up, this leg. How much is this leg? This leg would be 25 yt minus 7 y prime t, right? And goes up here, we got 25 yt minus what? 7 y prime t, and then plus 14 y double prime t. Okay, so over here we're gonna get y triple prime t multiplied by, hold on, what's y triple prime t? It's gonna be xt, right? Which is this one, xt goes in, and then plus 25 yt minus 7 y prime t plus 14 y double prime t. And then the whole thing multiplied by 0.1. Okay. Is that right? Am I doing it right? Oh, I'm doing it wrong. Because here, I forgot there is a negative sign here. So it's going to be x minus this whole thing, right? Okay, there's a negative sign here. Be careful there. Okay, there's a negative sign here. It's minus. Now, is it right? Okay. So we have what? Multiply by 10 on both sides. Okay. Yeah. Oops. Okay. Okay. How do we make it on it? Well, actually, this is what we have. Okay. I could multiply both sides by 10. Okay. And we move it, make it an ordinary differential equations. Okay. So we got 10. Okay. So we got 10 y triple prime t. Okay. And what? So 10 y triple prime t, and then move everything else. So we got plus 25 yt minus 7 y prime t, right? And plus 14 y double prime t. Okay, and equal to xt. Okay, that's what we have. Okay, for the differential equations of the form. Is that right? Okay, hopefully. All right, now, once we have this, okay, suppose we have this. Now we want to solve for zero input, zero state responses. Okay. Okay, let's talk about zero state, zero input responses. Okay, last time we learned about impulse response, right? And the output of the impulse response is called zero state response. Yeah, okay. Now we want to talk about zero input, zero state response. Okay, the zero input response of the system is the output signal when the system is driven by only the initial states. Okay, that means the input signal is zeros. Okay, no input signals. That means xn is becomes zero. The zero state response means the output of the signal when the system is driven only by the input. That means all the initial conditions are zero. Remember, if you got like the third order differential equations, okay, why you need initial conditions? Okay, you need to know the initial condition. For example, y0 equal to y naught, okay, y prime at 0, probably y1, and y double prime at 0, probably y2. Okay, you need three initial conditions for third order differential equations. Okay, so in this case, okay, all the initial condition must be 0. Okay, so y0 equal to y prime at 0 equal to dot 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 until yk minus 1 is 0 is 0. Okay, this is called the zero state response. And the total response is the zero input response plus the zero state response. Okay. What's the impulse response? Well, we learned that already. Okay. Impulse response is the output when the input is impulse, right? Is the unit impulse. Okay. Unit impulse as the input. Okay. Is the zero state response. Okay, when the input is result. And unit steps, okay, impulse response usually we use for the impulse response, usually we will use what notations? H, right? That means if you got systems here, okay, if you go in, this is LTI systems, right? If you go in delta T, what you get out is H of T, which is impulse response. If we input step response, okay, the UT. UT is when it's the unit step functions, okay, it's the unit step functions. If the input is the unit steps, okay, the output is called the unit step response, okay. So the output would be unit step response, we use S of T, okay. All right. And if the input is what? Any xt, right? Any xt, the output would be what? The output yt would be what? ht convolute with xt, right? Okay. So remember these pictures. Okay. Now let's solve the differential equations for the unit step response. Okay, basically this is what we have. Okay, the question is actually, okay, for the discrete time, you could find impulse response easily. Okay, but for the continuous time, normally we cannot find the impulse response easily. Okay, for the continuous time, h of t, okay, for the continuous time, normally h of t, we don't know directly if the input is delta function. Okay, for example, here, if we want, suppose if we want to find the impulse response, okay, suppose if we want to find the impulse response, what do? We put xt as delta t, right? And we yt would be h prime t plus h plus 5 plus 5 ht, right? But the question is, how do we solve for how do we solve for ht here? Okay. The question is, we don't know how to solve for ht here. Okay. Mm, okay. It's very difficult to calculate to solve this one, okay, because we cannot solve it recursively just like in the last, just like last week, okay, it's just like in the discrete time system, okay, you cannot solve for this, okay, so we go around and solve for HST instead, okay, so it's like this, okay, we solve for unit step response instead, okay, and since, okay, so from here, okay, since the delta functions, okay, the derivative of the delta functions, okay, since ut, okay, since ut is the what, integral, right, of the delta t dt, okay, since ut is the integral of delta t dt, okay, and the integral is linear operations, okay, the not the integral, delta t. We will do it differently, right? Since the delta t is the derivative of ut, okay. Since the delta t is the derivative of ut, then this h of t, okay, and the derivative is the linear operations, okay. So this h of t, which is the impulse response, would be the derivative of S of t, the unit step response, the derivative of the unit step response. Okay, so to solve for this is what we do. Okay, to solve for the impulse response, okay, we find, okay, we find ut first. Okay, so to solve for impulse response, this is what we do. Uh, we feed in, okay, we feed in UT, unit step signal, into the LTI systems. This is the continuous time LTI systems, okay, and we get out S of t. And then we got to take the derivatives by dt, and you will get h of t, okay? We do it in two steps, okay? We do it in two steps. Okay, we got the unit step functions, okay, find the unit step response, and then take the derivative of the unit step response to get the impulse response. Okay, so go ahead and do that. How do we solve for unit steps? Okay, there's a trick here too, actually. Y prime t, okay, when we learn, okay, this one you need background uh, in advanced mathematics. That's why this course you're supposed to have passed advanced mathematics. Do you remember how to solve differential equations? These differential equations. Anyone remember how to solve the differential equations? Hmm? Anyone? To solve LODE with constant coefficients, what do? We have what? The complete solutions equal to what? YC plus YP. Remember? Okay, this is called the complete solutions. And YC is the complementary solutions. And YP, what's the YP called?
Particular solution.
A particular solutions. Right? Okay. Okay. This is what we're supposed to do. Okay. Remember that okay. So this is what we have. Okay. And we want to feed in the unit step functions. So we have S prime t plus 5 st equals to ut. Okay, this is what we have to solve for. Okay, we have to solve for how I use a different s to distinguish it from the 5. Okay, to distinguish it from the 5. Okay, I don't want to confuse the s and the 5. Mommy. Okay. Okay. Okay, how do we solve for this? Okay, note here that since ut, okay, since ut start when t since, okay, ut is 0 for t less than 0, right? St would also be 0, okay, for t less than 0 as well. Okay, so from now on, we just consider when t is more than 0, okay? When t is more than 0, okay? Actually, when t is more than or equal to 0, okay? And it's supposed to be zero state response, okay? Zero state response mean there's nothing happen, right, before you start the signal. And ut is more than 0, okay? We can have s prime t plus 5 st. What is ut? When t is more than 0, it's 1, right? When t is more than 0, it is 1. Okay, so it's a constant. Okay, when t is more than 0, it is equal to 1. So it's just a constant. And you solve for this. How you solve for this one? Well, we find the complementary solutions, right? Complementary solution is when what? The output here is equal to 0, right? It's when the input is equal to 0. Okay, so to find well, the complementary solutions, remember, if you recall, right, well, the complementary solution is actually the homogeneous solutions, right? Is the homogeneous solutions. Okay. Okay, how about complementary solution is the solution to how about I write it, is the solution to s prime t plus 5st equal to 0. Okay, I use specifically, it's supposed to be 0 here. Okay, and what is, we assume yc to be? We assume yct to be e to the rt, right? If you recall, okay, and solve for r. So we got r e to the rt plus 5 e to the rt equal to what? R plus 5 e to the rt. And it's equal to 0. Therefore, r equal to negative 5. Okay? So in this case, our complementary solution is e to the negative 5t. Okay, that's step 1. Okay, step 2. Step 2, we solve for yp t. Okay, a particular solution, remember, since this is a constant, right? Since this is a constant, what do? We assume yp to be another constant a, right? Assume yp to be a constant a and substitute in back into the original equations with this equal to 1. Okay, with this equal to 1. So we're going to have what? 0 plus 5a equals to 1. So a is 1 over 5. Okay. Therefore, what do we have? We have yt, which is the complete solutions, going to be yc plus yp. Yc is, this is yc plus yp, right? Yc is e to the negative 5t. Oh, but it's going to be, yc is not just e to the negative 5t. It can be any linear combinations, right? It's going to be a constant k. times e to the 5t, okay, and then plus 1 over 5, okay, a constant ck plus e to the 5, and this one is our complete solutions, okay, and then you still need to find you can find k, the constant k, okay, 5k from initial conditions. Okay, from initial conditions. Okay, and what's the initial conditions? Remember, the unit step response or the impulse response is the zero state response. Okay, it's supposed to be the zero state response. That means initial condition is zero. Okay, so in this case, if you want to find ST, okay, to find ST, okay, we assume initial condition to be zeros, okay, we assume Y0 is 0, okay, or S0 is 0, same thing, okay, S or Y, the same thing, right? Okay, so in this case, you're gonna have 0 equals to k times e to the 0 plus 1/5. So k is negative 1/5. Okay. Therefore, we're going to have st, which is the unit step response, equals to negative 1/5 e to the negative 5t plus 1/5. Who's start sharing? Huh? Come on. Some of these. Can you see the screen I'm sharing?
no ครับ
how come ทำไมมันบอกว่ามีคนอื่นพยายามแชร์สกรีนกับผม แล้วเมื่อกี้เพิ่งดับไปใช่ไหม
ใช่ครับเมื่อกี้
เมื่อกี้ก็ไม่เห็นมีใครแชร์นี่มีคนมาแย่งแชร์สกรีนผมหรองงละ Okay, this is the unit step response. Remember that this one only valid, okay, only valid when t more than 0, okay, and is equal to 0 otherwise, okay, but we don't really need to write it, okay, we don't really need to write it there because we only consider for t more than 0 anyway, okay, but
Professor, you're sharing the Microsoft Team screen, not the note นะครับ
อ้าวเหรอ Microsoft Team screen not the note อ้าวเหรอมันยังไม่มาเหรอเอาใหม่ เอามายัง
ครับโอเคเห็นแล้วครับ
Okay, and the next step to find the impulse response, okay, we take the derivative with respect to t of the unit step response. What's the derivative of with respect to t of the unit step response? So we got what? Negative 5 times negative 1/5 e to the negative 5t plus 0, right? Which is e to the negative 5t. Okay, this is our unit step response. Okay, remember here, this one only valid t is more than, okay, more than or equal to 0. Well, actually, the reason I need to include 0 is because the impulse response like this, the impulse response, the real impulse response, right? The real impulse response is supposed to be like this, right? Goes to infinity and then stops, okay? So this is like, you should include the 0. So you should start at 0 minus, okay? To include something here, and the impulse response should include, there should be something happen and then die down. Okay, and this is die down as e to the negative 5t. In other words, ht is e to the negative 5t times ut. Okay, this is our impulse response. Okay, this is how we find the impulse response of the systems. The question is the system BIBO stable? How do you know if it's BIBO stable? We what? We see if it's absolutely integrable, right? If you integrate from negative infinity to infinity of absolute value of ht dt, which is what? Integral from 0 to infinity because it starts with ut, right? Of e, okay, and you can see that it's integral. What is it equal to? It's equal to 1/5, right? Okay, so it is stable, okay, which is less than infinity. Okay, so it is stable. Okay. And what's the next question? Find a zero state response. If you want to find a zero state response, you just convolute, right? When x equal to this, okay? So if you want to find the zero state response when x equal to this, you just have what? Just have yt. Just has yt equals to xt convolute with ht, okay? And so you get, well, you just can just convolute them together, okay? I'll let you do it as homework, okay? And the last one, I want to show how to find zero input response, okay? Okay, that zero state is easy, okay, because the you have found the impulse response, okay? You do it here yourself, okay? For part D, how do you find the zero? Okay, the zero input response is the response when the input is zero, but the initial is not. Okay, this one we have initial conditions y0 equal to 5. Okay, this is due to the input response zeros and y0 equal to 5. Okay, so over here we need y0 equal to 5. Okay, but the input's supposed to be 0. That means we are solving this one. We are solving what? We are solving y prime t plus 5yt equal to 0. Okay, this is when xt equal to 0. And y 0 equal to 5. Okay, and we already solved that, right? Which is what? We knew that yt is supposed to be what? Some constant k times e to the negative 5t. Okay, and what do we do? And then we substitute in y0 equal to k times e to the 0, which is k, and it's supposed to be equal to 5, so k is 5, right? So k is 5. So in this case, the y0 input response is 5e to the negative 5t. Okay, and the total response, okay, and therefore the total response would be, that's the last one, right? Yeah. Okay, finally, total response. the complete response. We call it the total response. Okay. The total response would be uh, the total response would be what? Y yt equal to y0, oh my, zero state plus zero input. We haven't, well, I see. Maybe we should do it differently, right? We could do convolution at these steps. Okay, here at this step, you want the zero state response, and then you do convolutions, which is going to be hard. Okay, which is going to be hard. You could solve it classically, classical methods. You can solve it by you can solve classical methods. Okay, you can solve for zero zero state response instead of doing convolutions. Okay, okay. Instead of convolutions, okay, we can solve for zero zero state response. Okay, from Okay, I'm sorry. It seems like I got disconnected. Is it still, is the recording still on?
I think the recording is still on ครับ but the
Okay.
screen is not shared ครับ
The screen is not shared. Okay. Oh gosh. Oh, where were we? Where did it got cut off? Where was that?
You said instead of convolution we can solve for zero state respondent. It just got cut out right there ครับ
Oh, I'm gonna show you. Okay. There are two ways to find the zero state response. Okay. One of them is to find the impulse response first. Okay. And then find uh and then use the impulse response convolute with the input, okay, to get the output, okay. And I'm not showing that to you because we did that already, okay. uh, so I'm going to show you the classical way, okay, the classical methods, okay. We can use the using the classical methods, okay. The classical method is the method you learn from what, from advanced mathematics. Okay, it's probably easier that way instead of using convolutions. Okay, so for the classical methods, we solve for yt. Okay. Oh, excuse me. Hello. ใช่ ไม่มีปัญหาอยู่ในห้องตลอดอืมใช่อืมปิดปิด
Mommy, mommy, mommy.
มี yeah. Okay. Okay. Yt. Hold on. What was that? What was the equations? Okay. Yt prime plus 5yt equal to xt, right? And this xt is this xt is supposed to be what? E to the negative ut, right? Okay. Okay. If you use the classical, okay. If we use the classical methods, okay, we can assume, okay, if zero state means you got y0 equal to 0, we can assume yp to be e to the a e to the negative 2t. Okay, we assume ya to be yp to be a e to the negative 2t. And then we just plug in to the equations and solve for a. Okay. This one we got what? Negative 2a e to the negative 2t plus 5a e to the negative 2t. And it's supposed to be equal to e to the negative 2t. Okay. Assuming t more than or equal to 0. Okay. So we got 3a, right, equals to, so a is 1/3. That's it, right? Yeah. Okay. 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 And then what do we do here? I see. Well, there are many steps, right? Y t would be some k, some constant k e to the negative 5t, and then we plus 1/3 e to the negative 2t. Okay, that's our zero state response. Okay, we got to have both particular solutions and homogeneous solutions, complementary solutions. But this one we assume find k using y0 equal to 0. Okay, yeah, we use k find k using y equal to 0. So we have what equal to k times 1 plus 1/3. Okay, so k is negative 1/3. Okay, so this one we can have negative 1/3 e to the negative 5t plus 1/3 e negative 2t. Okay, and that's our zero response. And the complete total response, zero state response plus zero input response. Okay, so zero state response is negative 1/3 e to the negative 5t plus 1/3 e to the 2t, and then plus zero input response, which is 5 e to the negative 5t. Okay, which is whatever that number is, 5 minus 1/3 is what? 5 minus 1/3, it's 15 minus 1 is 14, right? 14 over 3 to the negative 5t. That's 1/3 e to the negative. I think that's it. Did I do it right? And that's our answer. Okay. Oh well. I probably need to give you homework on that. Okay. Uh, okay, to practice. Okay, so that's answer all of them. Very difficult. Maybe I should not mix the unit step functions with the impulse response.
Professor,
Yes.
why is for the zero input response, why is the y0 equal to 5?
Zero input response. Oh, is due to this is given. Y0 5 is given. The state. Okay. It's given. You got
So,
to be 0.
so for the input response, we use y0 equal 5, but for the other, we use y0 equal to 0, right?
Yeah, for the 0 state, you let y0 equal to 0 response. But for the zero input response, okay, you have for the zero input response, you got input to be 0, and then it depends on initial condition only. Okay. But to solve for the complete response, you have both input and initial conditions. Yeah, it can be confusing, isn't it? Uh, yeah. The alternating existence required by this ones.
And in the input response, how did we get like the yt equal to k e to the power of minus t that fast? Did we get it from somewhere else? I'm not too sure.
K times e to the negative 5t, right?
Yeah,
K
yeah.
times e to the negative 5t, this is the complementary solutions. It's when the input is 0.
So like, so we get it from like when we were doing
The homogeneous solutions. We are finding the complementary solutions here. This is
okay.
the complementary solutions.
Oh, okay.
Okay. Mhm.
And we
So
don't have to,
basically, it's like the, yeah.
and we don't have to bring like the particular over, just the complementary.
You don't need the particular solution because the particular solution depends on the input. And if you want to find 0 input response, that means the input is 0. The particular solution it becomes 0. Okay. Uh, okay. Okay. Let me summarize this. Okay. The complementary solutions, okay, depends on initial conditions, right? Depends on initial conditions. The particular solution depends on input. Okay. So whenever you have initial conditions, you use particular solutions, right? Because the particular solutions, you got the complementary solutions, okay? The complementary solution is of the form k e to the negative 5t. And the particular solution changes with the input, right? The first input was unit step, your unit step functions, and you got particular solution to be what? To be 5, right? What was that? The particular solution was 1/5, okay? The particular solutions here, okay? The particular solution here is 1/5 if xt is unit step, right? But it changes to what? It changes to, uh, where was that? It changes to 1/3 e to the negative 2t, right? It changes to 1/3 e to the negative 2t if xt is e to the negative 2t ut. Okay, so the particular solution depends on the input. Okay, the complementary solution depends on the initial conditions, and there are two initial conditions, right? When y0 is equal to 0 and when y0 is equal to 5. Okay, when y0 is equal to 0 is called the zero state response. Okay, when y0 equal to 5 is not zero state. Okay, but when y0 equal to 0 is state response only if xt is equal to 0. No, no, no. Xt is not 0. Xt is anything, right? Xt is anything. Okay. If you want to find 0 input response, okay, you got y0 equal to some values, and then you got x equal to 0. Xt equal to 0. Okay. Maybe I'll summarize it a little bit more better next time. Okay. Then we need to do discrete time system. I think I'll skip that. Okay. Next time I'll explain this one instead. the second order. Okay, it will be more clear, I think. Okay, you can skip that. Oh, we have no more pages left. Okay, we still have 1 week on Laplace transform. Let's do. We're gonna do Laplace transform next time then. Okay, next week. All right. Okay, I think that's it, and I think the quiz has come up now, isn't it?
I don't see any นะครับ
ยังไม่มาอีกเหรอ
ใช่ครับ
ผมไม่ได้มัน
ยัง
เหมือนคราวที่แล้วเลยไม่ได้โพสต์ไว้เหรองงละตายละอ่ะถ้ามันไม่ขึ้นมาก็ไม่มีโอ้อันนี้ผมใช้ iPad อยู่มันเข้าไปไม่ได้เออมันเข้าไปยังไงวะเข้าไปในควิสเข้าไปยังไงอะต้องเปิดคอมพิวเตอร์ถ้าไม่มีก็ไม่มีมันต้องมาตั้งแต่ตอน11:40สิใช่ไหม Okay, I'm sorry. There's no quiz at the end of the lecture today, I guess. Okay, I'll see you next.
อาจารย์ครับ I have a question.
Yes.
For the communicative property of convolution, assume that we already have two signals. Can we assign any of it to be the HT, the impulse response, because it has a commutative property,
Yes.
isn't it?
Yes. That's right.
So we can choose the easy one to inverse it and shift it.
That's
To
right.
convolution, right? Okay.
Yes, that's right. That's normally I would normally do. Okay, I choose the one that I think is easier and flipped it, time reverse it. Okay, and then do convolutions.
And
Okay.
for LTI system, I want to make sure that if it is LTI, so it would be considered that it will be linear and time invariant, right?
Yes, it got to be LTI system to represent by the impulse response. And then you can do convolution. If it's not LTI, even if you know impulse response, okay, you cannot do convolutions. The convolution would not give you any answer. It will be meaningless. Okay.
And according to the explanation at the beginning of the class, so the causal, the LTI system that is causal need to have the t less than 0 need to be the 0, right? The impulse response
Yeah,
of the
should right. The delay supposed to start with 0. M naught and N naught supposed to start at 0
okay, thank
to
you.
be causal. Okay. Yes.
อาจารย์ครับ can you explain what our friend just asked the first question that he said something about it doing it easier? What was that? I did not understand.
Suppose I ask you to find xt convolute with ht. Okay. If one you got to flip one of them, right? You got to do the time reverse of one of them. Normally we will have to time reverse the second one according to the last one, right? Okay. But he says if he found that xt is easier to time reverse, okay, you can time reverse the xt and then convolute with ht. Okay, you basically time reverse the first one or the second one, doesn't matter. Okay, because it's commutative.
Okay, thank you.
Yeah.
So there's
because
no
it's
Oh,
commutative. Yes.
and when we do convolution, it is better to do it graphically, right?
Yes, actually, if you do convolution, usually I do it graphically. Uh-huh.
Okay.
It's easier to understand graphically. Okay. But if you can do it mathematically without graphing and correctly, I will accept that too. Okay, if you master it enough, okay, you could just write it in terms of ut, and then you say, oh, because you have ut and ut minus 5, then you got to integrate just from 0 to 5. That's fine too. Okay, some people can just do it, just writing the math without drawing anything. Okay, just like the one I did last time, right? But you kind of have to imagine what happened, okay, in your head anyway. Okay, so I suggest you do it graphically, okay, when you do convolutions. Okay. Anything else? I guess in the exam I should ask you to do it graphically. Okay. All right. Thank you. If there's no more questions, let's stop the recording. Wow, everybody's so applause.